Alright guys, let's take a look at element types. So for any given CAD geometry, we can go through a process called meshing, where we let the computer really run an algorithm that creates a solid mesh. So it discretizes this CAD geometry, which really just consists of mathematical description of the surfaces or solid bodies. It's not useful for any type of analysis. So in order to run anything that we are interested in, like solid mechanics, then we need to discretize it, which means we need to use the CAD geometry so that we get solid elements that are of a specific size that we can control, and where the aspect ratio isn't too messed up. All sides of the element need to be the same. That's what we strive after. Of course, that's not always manageable given the geometry. Well, in this case, it's pretty simple, so most of these individual elements have pretty much the same sort of side length. But in general, it's not always possible. Now, locally somewhere, the elements might be smaller than in some other places, and that's fine. That's really what we want. We want generally in places where the geometry doesn't change very much, we want it to be large elements that capture the overall deformation, but in smaller regions we want to have more elements so that we can resolve the stresses or strains or whatever sort of field that we are after, be it deformation or whatever. Now, there are several choices here of element type, and what we are seeing here could be they're basically tetrahedral elements, and what we are seeing here are so-called hexahedral elements. So these are sort of cubic elements, if you want. They don't always have that shape. They could have a sort of deformed shape a little bit. In general, these are better at resolving the fields that we are after mathematically, because of their basis functions are formulated a little bit differently, so that just using one more basis function, we actually get a much better accuracy than, for instance, using these elements, which have usually, like if you look at 2D, then there are triangles and they have 3 basis functions, and these have 4 basis functions, but these basis functions are so-called bilinear. So if you take the derivative out of these basis functions, you still end up with something that is smooth and linear, but in this case you just end up with constants if you have the lowest order, and that's why they're quite bad at resolving any field, and that's why we usually need to use higher order elements, especially of at least second order. But in this case we can get away with just using one. Now there are other things to take into consideration here. First order tetrahedral elements are just straight lines connecting each other. So they are they have 4 nodes in total, and it's just straight lines connecting them. And if you go to the second order tetrahedral element, then we have midpoints, and the side here is a quadratic. It's a parabola. That is this. Every side is a parabola, and that of course works much better for capturing anything that is curved in geometry like this. And that's where the power of the finite element method really shines, where you can have this discretization follow the geometry much better. And this is especially true if you have nonlinear problems, if you have contact problems or anything like that. It's very hard to do anything useful with these shapes here. Alright, then we have the alternative. These guys are very good at approximating whatever they want to approximate, but the problem is geometry. It gets very cumbersome to in a meaningful way create an algorithm that automatically generates a mesh. In the earliest days of the finite element method, this was done by hand. Engineers would be doing the meshing. Nowadays, computers do that, but it's still hard, even for a modern software to do this. Mostly for our linear problems, the most time spent on an analysis is the meshing part. So it takes much longer to actually just discretize the geometry, to go from the CAD model to a meshed model, than it is to actually solve the problem later with all of the stuff that you have been doing, creating this linear matrix system and solving it. That is just a fraction of the time it takes to actually do this meshing, and especially using an algorithm to do it using bilinear elements or these quadrilaterals. That's especially very time consuming, and sometimes it's not possible to do it everywhere. So in some cases you might end up with triangles where you need to connect certain regions where it's not feasible to do it with all of these quadrilaterals. So these sort of triangles are connective elements that we usually call wedge elements, but they're basically just triangle elements which we need to use. And of course, in that region, the approximation will suffer. It's not going to be the same order as the rest. So yeah, you need to take that into consideration. And especially if you sort of model anything useful in 3D using these elements, and you need to resolve some certain areas here using them, then it becomes very, very hard, because it's very hard to do any adaptivity like we see here, when we have mesh adaptivity, when we have regions where we require a much higher resolution, and to make this transfer, it's quite hard. Now let's take a look at what type of elements we have. So in 1D, you have already seen we have this just linear element here. We can have quadratic elements as well, but in general we have this every degree of freedom here is just being able to, well, live in a one-dimensional space. So every degree of freedom can move in one direction, and in this case we have only 1 degree of freedom. It's just this thing here which can move. We sort of have a function value attached to these in one direction. But of course we could have a one-dimensional element. It's one-dimensional, but every node is allowed to move in either 2 dimensions. So we can have 2D, so x and y, or we can have 3D, which is x, y, and z. If you want a physical analogy, this could be a spring in 2D or 3D. And then we have 2D elements. And 2D elements, we have the triangle. That's our basic element. And again, this thing can be living in 2 dimensions, but it could also be living in 3 dimensions. So this could be in 3D space. So every node here in 2D is only moving in x and y, but in 3D it can also move in x, y, and z. And that's typical for all of these elements. And then we can have higher order elements. And for 1D, we've already been talking about this for a while, but now for 2D we have the second order triangle here, and that can be curved, so every side is a parabola. And we can have the second order quad, where every side is also a parabola. And in 3D we could also have one node in the middle, making this thing really curved in 3D space as well. And usually we have 2D elements in 3D, then there are shell elements or membrane elements. So the reason we have these type of flat elements, if you want, where the thickness is 0, in 3D is to simplify the computations a lot. Because the alternative is to use three-dimensional elements in order to model something very thin. And that means you need to have a lot of elements. Remember, these things can't be squished too much. So you cannot squish these and have one side be much longer than the other 3 sides, for instance. That's very bad accuracy there. the Jacobian will be very badly scaled, and that just leads to a unstable matrix system and bad accuracy in general. So you need to avoid that. Thus, we are left with either having a bunch of elements to model something like a car roof or something very thin, or you need to switch to a lower dimensional element here that lives in 3D. So for instance, we can have 1D elements, we can have beam elements, and they are typically not R1, they are really R2. So every node here is at least has 2 degrees of freedom, but really they have 3 or even more. They have 6. So beam elements usually have 6 degrees of freedom. So what you can do is you can translate every node in X, Y, and Z, and you can rotate every node in 3 axes. So 6 degrees of freedom. That's a typical beam element. But now we have beam constructions everywhere. We have beam designs everywhere. And if you're designing stuff out of beam, the truss works, and they are defined by being welded. So at the connection points, they are typically welded, which means that when you're deforming such structures, you can, if you're looking at intersection point, then they are always going to have the same shape. So a beam element is usually deformed away from the connection point. And we use them very much, in fact, because they are quite accurately modeling what is happening in a truss works without the need of having to resort to these many elements, solid elements here. Because, beams are typically thin and very long. So you have one dimension which is much larger than the other dimensions, and then you need to do the simplification. And I'll be talking about beam elements shortly, because we will be doing some SolidWorks stuff with beams. But we typically don't want to generate a huge amount of 3-dimensional elements when we're dealing with 1-dimensional entities or 2-dimensional entities. And that's why we have these. And they can model different things. They can model shells, so they have bending resistance, or they can model membranes, which are like cloth. They don't have any bending resistance, but they can only take tension. And the classical type of element is, of course, a solid element, which is mostly used for most things that are solid. And we have the tetrahedral element and its higher order equivalency here. And we have the hexahedral element, and it also has high order stuff. It works the same way as the second order quad here. And then we have cake or wedge elements, and those exist to sort of connect, because this one side here can attach to a hexahedral element, and the other side here can connect to a tetrahedral element. So they are sort of used to wedge these two elements, because sometimes it's not possible to discretize your geometry using only hexahedral elements, because those algorithms are quite expensive and sometimes just hard or not feasible. So that's why you need to do tetrahedral elements in some places, and then you connect these using the cake or wedge elements, because these are of lower accuracy than the hexahedral element. So there you have it. It's a huge amount of different elements, and each has a corresponding basis functions attached to it, and each really has a corresponding quadrature scheme attached to it. Usually we can use the Gauss function that you have seen, but there are often more elaborate Gauss quadratures. Remember, we are trying to integrate with as few Gauss points as possible, or rather integration points as possible. That's why there's a lot of research which is happening and has happened in that area to sort of integrate this stuff exactly using lower order quadrature. All of these elements have local support. That means that every basis function is 1 in its node and 0 in all other nodes. So it's important to have local support because we want to keep the bandwidth of the matrices as small as possible. That means that every matrix has a certain amount of spread along the diagonal, and the bigger the spread is, the more memory requirements and more computational power we need to solve that equation system. So that's why it's very important to keep that as confined to the diagonal of a matrix as possible. So that's a reason why we have this property. But in the latest time, we have actually seen that there are new computational methods really that are not the typical finite element method approach, but they are using the underlying CAD mathematics in order to do the actual computations on that. So the basis functions are this high order Bernstein functions, and they work quite well. There are some very promising results there, but it hasn't really lifted off yet and become commercially viable. There isn't, for instance, any sort of programs which are utilizing that yet beyond the research stage, and there are sort of there's another side to that as well, negative side, which is that these matrices become very, very spread out because there's no local support anymore. The support is much, much higher. So every basis function is affecting elements that are far away, and that's a little bit of a problem. It becomes sort of expensive to run it on one hand, but on the other hand, you need much fewer elements or patches because they are working with CAD patches to solve a problem using that. So yeah, but we need a different approach for CAD anyways when we are using them. Usually we need T-splines in order to get that working, and not this boundary representation that we're using now. So yeah, so there's a lot of stuff happening around that, but it's very interesting, and there's a lot of really good researchers working on that. So the results that are delivering are quite promising. So we'll see what happens there. But usually the industry is using this standard stuff that's not fancy at all, and yeah, so that's the big industry is using just the well proven stuff that is just very, very standard. Let's take a look at this parametric mapping 2.mlx file here. What we're seeing here is a triangular element. If you see here, there are 3 nodes connected to each other in XY space, and what we see here in the Z space is that the function value is 1 here, or the Z axis goes between 0 and 1. And if you look at the legend here, we can see that we have 3 sort of basis functions here, blue, red, and green, and those are the ones that we can see here. So the blue one here is plotted, and it's very visible here that it goes from 1 in this lower corner here, and it's 0 in all others, and that's this partition of unity, or really the definition of a basis function being 0 in all other nodes than in its own node. And in fact, here we can see that we have a the number for it is 1, and these node numbers here are really 1, 2, and 3, and it's 1 in its own and 0 in the others. And for this one here, for the red one, we can see that it is 1 in this second node here, and it's 0 in the other 2 nodes. And the green one is 1 in its node here, and it's 0 in the other nodes. So that's the definition of the basis functions. And yeah, apologize, I couldn't really plot this without plotting the whole plane, really. So it looks a little bit weird, but that's what it is. take any point on this triangle here. So we take this random point here, which is at 0.3 and 0.2 in the x and y. And if we evaluate the blue function here, we get a sort of a height here. And we evaluate the same point in the red function, the second one, we get this red point and the same one in the green point here. And if we stack them all up, we will get this black point, which is always going to be 1. So no matter where we do this, we will get this black bar, which is the sum of the evaluated points in all 3 basis functions, and it will always be equal to 1. And that's the partition of unity property that we want this basis function to have. Now, we will start by just deriving the basis functions for these elements. And just go back and refresh your knowledge on how we did this for one dimension. It's very much the same here. So it's always good to visualize stuff. That's how my brain works, at least. I like to have visual cues on for everything. So we will take this standard unity triangle, which has a first node in the point 0, 0, second point in 1, 0, and third point in 0, 1 here. So that's our unity triangle, and we will plot it like we do here. And in fact, we can see this triangle on this side here, and we have sort of we create this patch which will create the outer geometry, and we plot the marker face colors here. So the markers are just plotted here, black, and then we sort of set the font size, and then this stuff here is we compute the midpoint, and what we're doing here is basically creating a vector going from the points towards this midpoint here, and at 20% along this way we plot our numbers 1, 2, and 3. So that's just a fancy way of sort of aligning the numbers a little bit. Now we make the same ansatz which we have done for the one-dimensional case, but in this way it's in this case it's a triangle, so we really need 2 functions here. We need x and y, and we make this linearly, so it's x and y is just linear. So we have to have a this a1 here, this parameter, which is just the constant parameter, and then for every x and y here we need to have an additional parameter. So this is the easiest basis function here. It's the simplest basis function really, and it's the linear one. Alright, so that means that we need to determine these 3 constants or parameters here for this 3-noded element. And we will again use the definition of the basis function. It's just that we modified this slightly. It's now a function of 2 parameters rather than being a function of 1. And if we set this to 1 and 0 for our all other coordinates here, so we're using our coordinates which we had, and we are setting this to 1, the first one, and it's going to be 0 in all others. So we're using the definition to sort of force this to be true. Okay, so this equational system will lead to this matrix system here, this linear system, or on matrix form it looks like this, and this way we can get our values for a by just following the same steps we have done before, and then once we have a, we can just define the basis functions by inserting it back into the function. Alright, and using MATLAB this can be achieved using this way here, and we get our first basis function like that. So we have 1 minus x minus y. For reasons unknown to me, MATLAB likes to use y before x here. Never mind that. Okay, moving on. The rest of the functions can be get by just generalizing this slightly. So instead of doing it one by one, we can just throw this into a C matrix, and using the same method as you have done in 1D, we can get our phi basis functions like so here. And then we do the definition test here to see that it is in fact true. Okay, now we can define other shapes. For instance, we have this quadrilateral. So we have this polynomial, we have this polygon here, which is just this unit element here going from, we have the first node in 0, 0, 1, 0, 1, 1, and 0, 1 here. And again, we just do a routine to visualize this. And then we make this ansatz here. So we have our basis functions out of the vector x, which is x1, which is x and y. And then we have at a1 plus a2x plus a3x plus, and then the third one here is a combination of both. We have x and y here. It's a multiplication of both of these. And that's our ansatz here. That's what we're doing. And just following the same rules again, we end up with our basis functions for this very element here. And now I'm sort of converting this into a MATLAB function, which you can see here or here, just for it to be much more easier to copy. Okay, so that's one way of deriving basis functions for this bilinear element. But there are other ways to do this, and it's much more sort of intuitive, if you want. So you can take, they are one-dimensional. So you have the basis functions from x here, and you multiply them with one another. So you have one for x, and you have the same ones for y, and you take the multiple out of them. And that's why it's called bilinear, because it's two linear elements. Bi means two. So you have one of the basis functions, then you have this combination of the first ones, and then you have a combination of the second one, and a combination of the third one, and so on. So you have a combination of these linear elements, and you get the same formulation back here. So if you just sort of expand this, you will end up with the same stuff here. Okay. And the same reasoning you can do for third order. So if you want to take this and multiply it again, so one more, but in the z direction, you will get the same thing, and then they are in fact called trilinear. So they are third order. So you can either do it this way or this way. I find this to be a little bit more systematic than this here. So yeah, you have that. You just need to sit down and think about, okay, how many do I have here? So I have x and y, and then I have a combination of x and y here. Yeah, for the fourth sort of corner. Okay, moving on. We have these basis functions in the parametric space. Why? Well, we never want to create this thing for any other than the 0, 1 space, or our parameter space. It doesn't really need to be 0, 1. It could be -1 to 1 as well. In fact, it is so in many books. So I've just chosen 0 to 1 because I find it more compelling in some way, because I have 1, it's 0, and then everything becomes a little bit more simple. The space is, for instance, it's the area of this triangle here is 1/2, so it's sort of going from 0 to 1, right? And especially for this one, the area is 1 instead of it being, well, if it goes from -1 to 1, then we have 2 times 2, so it's in fact 4. So you have to think about that all the time and such. And another reason why I like this much more is that the integration by hand becomes much easier, because I don't need to think about the lower bound and take that into consideration. Not that I do much stuff by hand now, but in the beginning of time I did, so that's why it sort of was easier. And I don't really feel that it's any difference. Like I don't see any reason why I should use any other range than 0 to 1 when it comes to, for instance, the Gauss integration. It's very easy to define the Gauss points in the range 0 to 1, and I don't really see a reason why I should use -1 to 1, and why it's sort of more elegant to do it anyways. So that's maybe just me, but yeah, I'm a unicorn. That's how I feel like. Deal with it. All right, so we have the basis functions defined in 0 to 1 space, and this is what we called the xi space here. And then we need more Greek letters. We want to do this in 2D or 3D. So we use the Greek letter eta here, and in 3D we have an additional zeta Greek letter here to define this parametric space. All right, so these are basis functions for the triangle, 1 minus xi minus eta. And yeah, and if we take the derivative out of this basis functions with respect to xi, sorry, here, defy xi, we will get what? We will get -1 here, and we have 1 and 0 here, so that this is this vector. And if we take the derivative out of phi with respect to eta, we get again -1, 0, and 1. So these are the derivatives of the basis functions. And in 2 dimensions, we call this the gradient of phi. And this has a special symbol. We just usually denote it with b. So this is a sort of the B matrix, or B hat, really, because it has to do with the parameter space. But I haven't really denoted this. I just called it the gradient of phi here. All right, and this is also something that we usually pre-compute. So we need the phi, we need the gradient of phi, because when we are dealing with solving, well, in anything really, we need the derivatives to do this, and we'll get to that very, very shortly here. So that's the parametric space, and then we'll of course have a higher order element here. So we just have mid nodes in the midpoints here, and we use the same reasoning. So we have the linear element here, and then we add higher order terms. So we have x squared, we have x squared times y squared, and we have y squared here. So this x squared, y squared thing is really in this node here, the 5th node, because it's sort of in the middle of the element, and we have both of them are affecting it. So yeah, and using the same way we get at our basis functions here, and if we throw in the values, nodal values, and evaluate it, we get back this nice looking identity matrix thing here, where the sort of definition is reported back, and then that's okay. And we can have quadrilaterals as well here. As I showed you before, it's the same way. It's just that we call this now xi and eta. And higher order quadrilaterals, you can see them here, and how the ansatz looks like. And we can go higher order as well, and in fact I have some such thing at some other point. And this element here is called the serendipity element. That's another name for it. Alright, so enough about elements and how they are formulated. Now let's take a look at what we can do with these. So in fact, what I want you to do in your first org packages is some simpler version of this here. So it's about interpolation. So iso-parametric interpolation. So we have this triangle just in xy space, and that's what we call usually the physical space. And the 0,1 space here with xi and eta we usually call the parametric space. So in physical space, some random triangle is living there. And we have at the corresponding nodes, we have some sort of temperature field here. So we have this temperature field at node 1. The temperature is known to be -1. At node 2, the temperature is known to be, well, 2. And at node 3, it's 3. So yeah, so that there's that. And if we patch this, if we use this patch here with the face color set to interpolate, and the color data, C data here, being hue, then this patch function will interpolate the color for us. So we have this linear interpolation. It's always going to be linear, sort of giving us the color. And for a triangle, it's very accurate. It's exactly what it is.
And each time we have such colorful picture, we need to have a color bar telling us what these colors represent in terms of values. Alright, so what is the point with this? Well, we want to evaluate what is the temperature at some parametric point here, xi and eta equal to 1/2 and 1/3. So in our triangle, if you have a picture out of this, if we are now going from the parametric space in this point to the corresponding point of this physical triangle here, and we want to know what is the temperature at this point. And the way of solving this is by using the basis function evaluated at exactly this point. So we have our function here, phi of xi and eta, and if we multiply this with u, so we're interpolating u. Now using our basis function here, we have our capital U, which is the interpolated function. It's a function of xi and eta. And now we set xi to 1/2 and eta to 1/3, according to the problem that was given there. And we substitute this in, and we get our values. The value at this point is 1.8 something something something. And you can plot this point here. In fact, that's what the first work package is all about, or the first or second problem in the work package, I don't remember. But it's just figuring out at this point here, what is the corresponding physical point in physical space. And the way you do that is just by interpolating the actual points. So instead of interpolating some function u here, we are the nodal functions u, we are in fact interpolating the actual the actual points using phi. And we get back not one value, but we will get back in fact a vector. And that's exactly what we can do here. So I can find out this point by just taking phi here and multiplying this with p. And I can do that because, well, phi is a 1/3 vector and p is a 3/2 vector. So what I will get back here is, I call this capital X. I will get an expression for x of xi and eta. Alright, now xi and eta is already set, so I can just substitute this. So I can write subs x here, and I will get my values. And if I want to have this in decimal form, I can do this and just set it, let's do 2, it's okay. So this is at point 1.2 and 0.67. Alright, so let's plot this. We can do plot, and in fact let's call this I don't know, yeah, let's call it xp. Alright, so I'm plotting xp, I'm plotting the first element of xp, which is the x component, and the second here, and I'm going to denote this with a black K star. So my point is come on, why don't you work? Yes and yes. So yeah, sorry, yeah, xp is now a function. Well, that's not good. Yeah, I don't want this to be a function, so I'm gonna convert all of this back to a double instead. Now I can make sure that this is a number. I don't need this to be symbolic, and I have my point exactly there. So that's my point, and I can sort of show this other thing using patch. And I have, well, what I have 0, 1, and 0, and I have, that's 0, 0, 1. Just set this to white and a new figure. Yeah, so this is my element. And because I'm a lazy man, I will go back here and just grab the code for visualization out of this. So this is what I have. Take the whole thing and just dump it here or here. Like so, and now here I will add my point. So I will have this xi and eta point here, xi and eta. So just xi and eta, and denote it with a, again, a black star. And it's not p, small case p perhaps. 0 0 1 0 and 0 1. So smaller case p. Okay, so this is my parametric space here, xi and eta, and this is my point. And this point is, I can sort of denote this point. I can write text at this very point, xi and eta. And my text is going to be, well, xi and eta. And I believe I need to do this backslash and backslash. And yeah, let's do it like this. Xi is equal to, what was it? It was like 1/2 and 1/3, right? Right? Yeah. So if I run this, I get at that very point I have this. So let's just offset this slightly, just minus 0.1, 0.05 perhaps. It's enough. Just to offset it a little bit. There we go. Yeah, so you can do this programmatically like I did, or you can actually add annotations to this. Let me show you that, because, well, why not? Some of you are proper and want to do this correctly. So you can sort of insert a text box wherever, and we can write \xi and enter, or click away, and then you have your xi. You can right click on this and just do, yeah, the line style can be none. Get rid of that, and you can do well, font, and you can change properties here to something. And if you double click on this, you can write 1/2, for instance, like this. Or if you want to be mathematically, you can do frac and 1, and this is LaTeX. Come on, there we go. Like so, and it's not going to know what this is, so you have to change the interpreter to LaTeX, and now it will not work, because we need to, if it's LaTeX, then we need to actually have these $signs around it, and now bam, it works. So it's a nicer way of writing this stuff. So we have this, and then we have eta is equal to, and again frac, and we have 1/3. So yeah, so there's different ways of doing this, and this is just the text, so you cannot really yeah, maybe you can do stuff with this, but this is an annotation. And if you right click, you can show code, and we'll get code for this, and we can see here that one of these is a well, we have text here, and for the other we have both our texts. Wow, that's interesting. So it doesn't really, in this new version, it has created text for both, which is interesting. Usually it was annotation. Well, that's something. I didn't know that. Yeah, so you can use this to get code generated for you, but you can always save this function, which we have now. You can save this as a fig file, .fig, and it can be opened, and you can access all of its data and yeah, change properties and whatnot. You cannot get this back into the into LiveScript here. Unfortunately, it sort of vanishes in some other MATLAB window. So that's quite sad, but yeah, if you want to use it, you can. Yeah, you see the aspect ratio is all messed up here. We can fix that. But if you want to use it, you can take a print screen out of it. So I can first fix the aspect ratio by writing x is equal in the command window. And then I get this, this proper equal aspect ratio. And yeah, from here we can sort of, we can change the fonts to a larger size and make it more visible, and then you can just use your favorite tool for well, taking print screens and throw it in to your thing here, to your report, to the LiveScript, and then maybe write something about it or whatever. So yeah, short story long, that's how you do it. All right, so that's example 1. Really, I've just pasted this in completely wrong, so let's just get rid of it. That's example 1, and for example 2, you are now doing the opposite thing. So we are, in fact, we know that we want this temperature at this particular point, so it's not straightforward like it was here. It's much easier to interpolate something when you know what the parametric point is. But in this case, we don't know what this point corresponds to, this xy point. And the first thing we need to do is to figure out, all right, so we know a point in physical space. What is this point corresponding in this space here in order to be able to interpolate whatever field we want to interpolate. And that's not possible easily. We need to solve an equation system. So this is our point, and this is equal to our xy point here. So take phi, multiplying with our points, our coordinates for the triangle, and we get this expression for xy. So this is our x coordinates out of xi and eta. And we set this to be equal to 0.5 and 0.8. So we get this equation system here. And in fact, we can transpose this just to make it more visible. So we have this equation system, and now we need to solve this for xi and eta. And if you do that, just the easiest way possible here, we get our point back in the parametric space. And now in the parametric space, we can use this point to create a approximation, and if we insert this point here, we get the value at that point. So we have our point, our starting point. We have the corresponding point after solving this equation system here. So let's do that. So our lower case point here, p, it's always going to be this. So like so, and we have eta and xc there. So let's take a look at that. So yeah, so that's our point, and that's not 1/2. So let's just get rid of this text box thingy. All right, so now we're going from our physical point, which is given here. It's 0.5, 0.8. So this is our physical point. We are computing the corresponding xi eta point in the parametric space in order to be able to evaluate the where am I here? In order to be able to evaluate the approximation of u at that point. So it's straightforward to go from the parametric space to the physical space, but the other way around, we need to solve a linear system. Okay, then we have the third example here, which is to compute the area of some element. And that integral is the easiest integral. It's just computing dk here from of dA. So we need to look at the isoparametric mapping of how this is done. And we will be using Gauss to integrate this. So no int business here, we will use numerical integration. So, all right, so we have this this polygon. We have this polygon here, and we want to know what its area is. All right, so this thing is a fourth noded element that makes it a quadrilateral, and we will use those types of basis functions. So first we will compute the area using poly area, because we can, and there are straight lines, it's a polygon, get the area, easy. Okay, you can do this analytically as well, but just, you know, this could be a rectangle, and then we have a triangle here and a triangle here. You can easily compute that, no problem. But that's not really the point. We want to compute it using this way, because we can later compute elements that are of this shape, which you cannot. I mean, you can give it a try, but yeah, you will not be able to compute this any other way than using this. You can sort of yeah, no, it's not gonna be possible. You can approximate it, but you will not compute it exactly. But we can, using the determinant of the Jacobian. So we need to compute the Jacobian here, because that's really what is. So the determinant of Jacobian here is telling us something. It's telling us, if I bring out my equation business here, yeah, I can do it this way, and let's just make this sticking. And this guy here, this is the sort of area change. This is the area change. This is the determinant of the Jacobian. It's telling us how much is the area changing from the reference element, that's k hat, to the physical element. So the reference element in this case, which is a bilinear, and it goes from 0, 1 to 1. The reference area is just taking the unit or the parametric element and computing its area. So for a triangle, it's going to be 1/2, obviously, because, you know, it's 1/2. And for a quadrilateral, it's going to be 1. So in this case, the determinant of the Jacobian is the actual area, because it's sort of mapping 1 to 1. So if you compute this, the determinant of the Jacobian, we will have the area. We don't even really need to integrate it in quotation marks, but we will do that as well, probably, right? Right? Yes. No? I'm not doing it using Gauss. Yeah, I'm here. Okay, never mind. Yeah, it was a long time I wrote this. Okay, so we need to compute the determinant of the Jacobian. So that means we need to compute the Jacobian. And computing the Jacobian is quite straightforward. So we have these this business here, dx, 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 d eta, and that kind of stuff. That's easily computed, because in fact we take the derivative using the chain rule, the derivative of the basis function, and we multiply that by the coordinates of our element. And the derivatives of the basis functions, that's what we call b hat, and we take that and we multiply it using the coordinates of the element, and that's our Jacobian right there. So this here is going to be a 2-row by n, where n is the number of basis functions for our element. In this case it's 4, so 2 by 4, and this is multiplying something that is 4 by 2. So the end product is going to be 2 by 2, which is the Jacobian. Yeah, just to do the dimensional analysis. Now we usually copy in the numerical basis function here on this form, and then we can convert it to a symbolic. And you can do this because there's a file called basis functions where most of these are available to you, so you can just copy paste that in. So in this course we're all about copy pasting, but we need to write what we're doing as well. So yeah, so we have now a sort of symbolic expression for the this thing here, and we can take the derivative of this with respect to xi and eta, and you can copy this in as well, but it's a good thing to do to work out by hand and in MATLAB like this, just to confirm. But yeah, do all of this by hand. It's very good for learning. All right, then we define b hat to be this vector of vectors. If you want, we have the derivative of our basis function here with respect to xi and with respect to eta, one under the other, exactly like we have stated here. And what we do now is we take this matrix, the b hat matrix, and we multiply it with our coordinates, and that's our Jacobian. So the Jacobian is telling us how much this thing is. It's a map, really. So it's telling us how much is x changing with xi, how much is y changing with xi, and so on. And if you sort of take the determinant of that, it's going to tell us how the change of the area is. So how much is one area unit in real space compared to the physical space, compared to the parametric space. So we just take the determinant because there's a determinant function built in MATLAB. Matrix Laboratory, of course, they're going to have lots of linear algebra tools for us. So it's as easy as that. And the determinant is this, and now we evaluate it in xi and eta. And yeah, which xi and eta really? Well, we take the midpoint, because it's a linear function, and we can use Gauss, first order Gauss, to do this. So first order Gauss for xi and eta, it's the same point, it's just the midpoint for both of them. So this is evaluated in 1/2 and this is evaluated in 1/2. And the weight for 1 point Gauss is 1. So it's very easy, straightforward. So the area turns out to be 0.55. And that's exactly what we have confirmed in the area geometry here as well. So it works. You have confirmed it using a other known method. So now that we know that it works, we can use it to do other stuff like this here. This is a second order thing. It's we give this points. So these black points are given, and the geometry will be as follows here, because all of these sides here will be parabolic. So here is the second order triangle basis function, and we turn this into a symbolic value. We take the derivative out of that. It's a horrible thing, I know, never mind that. And you just multiply this thing with p, you get the determinant. It's this thing. Now this is really where the border of doing things by hand is. Like, I don't expect you to do this by hand. But take a look at what we have here. We have this third order polynomial, right? So in order to solve this, or to numerically integrate this, we need a third order Gauss rule as well. And this is what we have here. This is no, not third order, but second order Gauss rule. So this is a second order Gauss rule here. This is taken from some source. I don't really remember it, but it's basically says that the second order Gauss rule are the midpoints of our parametric triangle, and the weights are just 1/3. So this works. Remember that the space for our triangle, the area of our triangle, is 1/2. So we need to multiply the determinant of the Jacobian by 1/2. because that's what the determinant of the Jacobian is scaling. It's scaling our triangle, which has this area. So dk hat, that's what I call this. All right, and we do this using a loop, and you can just do it using just matrix multiplication here. I'm using a loop to do this, and our area becomes 0.67-ish something. So that's what we have. Yeah, and I had earlier some function here where I could, yeah, just for confirmation, but this really was a written function using the same method, so there's not really a point of confirming something using the same method, so never mind this, but it's sort of there as a reference to something we did earlier.